we'll start just by going over the syllabus. There's not a lot to talk about here, so but there is a lot to cover in this class. So I will, we're gonna have a short lecture today. I know that's kind of a bummer sometimes. You like to just have a syllabus day and go home on the first day, but we'll ease into it. Maybe it won't take the whole time, but we're gonna have at least a short lecture today. So I guess I'll start just saying a little bit more about myself. John Foster. This is Advanced Geomechanics. I have not taught this class since 2015. So it's been a while, but I have taught it. I'm kind of excited about that. Best way to learn something is to teach it, and I might be a little rusty, so you got to give me some grace if you let's learn it together, or in my case, relearn it. However, I really know this stuff well because I've used it my entire career. I guess I want to forewarn you, if you think this class is going to be something like just a more advanced version of the undergraduate geomechanics, it's not, okay? When Dr. Espinoza, who usually teaches the class, that's kind of how he teaches it. So it's a lot of like applications of wellbore stability and faults and things like that. We're not going to do that. What I'm going to teach you is something that's actually more useful, I think, and that is the more general theory. And so the first, if I could rename this class, and, it's not that easy to rename a class at UT. It's like a 2-year cycle and the whole thing, so usually it's not worth doing. But if I was going to rename this class, I would rename it Theoretical and Computational Geomechanics. Okay? So we're going to spend the first half of the semester basically learning the theory of continuum mechanics. Has anyone had a class in continuum mechanics? Yeah, you just took it last semester. Yeah, right. So, basically, we're going to learn the continuum field equations, or essentially conservation of mass, momentum, and energy. I always like to say, if you know those three, you know all of engineering. All of engineering is it's 4 equations. Conservation of mass, conservation of momentum, conservation of energy. What's the fourth one? Second law of thermodynamics. If you're an electrical engineer, there's Maxwell's equations. You'd have to add those, right? But for most of us, for all of us aside from electrical engineers, all of engineering is just 4 equations: conservation, mass, momentum, and energy. And so we're going to basically focus on how do we derive those for a continuum that is like an arbitrary continuous body, and that's what we're going to spend the first half of the class doing. And then in the second class, we're going to look at the computer implementation of those equations, or specifically conservation of momentum. But the computer implementation of the rest of them would follow the same way. But we're going to focus on conservation of momentum, and also mass, to basically derive the equations or solve problems with equations of poroelasticity, right? So poroelasticity is, you have a pore fluid, and that pore pressure, the pressure by the fluid, it imparts some stress on the solid body, and they're coupled to each other. Of course, if you deform the solid body, the pressure goes up. If you were to say squeeze the solid body like a sponge, then the pressure would go up and the fluid would move. And so you have to solve those field equations in a coupled way. And that's our goal by the end of the class, to have a computer implementation of the poroelasticity equations. And we're going to learn everything we need along the way, right? So we're going to start with the continuum mechanics, and then, about halfway through the class, we'll have a midterm. I'll go over the structure of the class. About halfway through the class, we're going to have a midterm that kind of covers all the continuum theory that we've learned, and then we're going to switch, and we're going to learn the computer implementation, and specifically what we're going to learn is finite elements. So we're going to look at a finite element implementation of the poroelasticity equations. And so there's a lot to cover in the class, and because of that, when we do in the first part of the class, I'm basically going to take this just-in-time approach to teaching. So if you were to take a continuum mechanics class, like a full course in continuum mechanics, you'd probably spend the first week or two basically covering vectors and bases and indicial notation, and you'll have to do these indicial notation proofs. We're not going to do any of that. I'll teach you the indicial notation even today. We'll get to some, but we'll talk about it as we go, and things like that, right? And I'm assuming that all of you know what vectors are and tensors and things like that. But we'll refresh them as we go. Okay. If you go to the Canvas page, take a look at the syllabus. There is a rough outline here of what we're going to cover. We start with kinematics and strain, and then stress, and then the governing equations of continua, and elasticity, plasticity theory, and then eventually poor elasticity theory. And then we'll have a midterm, and then we'll start with the computer implementation after that. So the grading structure will be like 20% midterm, 20% final. The final will probably be a final project, not a written exam. The midterm will be a written exam because it's theoretical material. It's like hard to test you any other way. So the final will likely be the final project, and then of course 60% of the class will be homeworks and computer projects. I expect maybe 6 assignments or something like that. Again, first few will be pen and paper theoretical assignments, and then in the second half of the class there'll be computer-based assignments. Right? There's no book for this class specifically, but I list a lot of sources there. This book right here, Malvern, Introduction to the Mechanics of Continuous Media, 1977. That's kind of the Bible of continuum mechanics. Most of the notation that we'll use in this class comes from that book. And the reason is notation matters. It doesn't really matter, but it matters in the sense that because it's kind of the standard, like I would say the vast majority of papers that you're going to read are going to use notation from that book. And so it matters in the sense that it helps you read papers faster, right? If you can just look at a paper and within seconds you understand that they're using the symbol F for the deformation gradient, which is pretty much everywhere, that's what people would use, then you just know, okay, that's the deformation gradient. You don't have to go look it up or something like that, right? So we're going to follow the notation of Malvern, but there's a lot of other books. This one right here is actually a book on finite elements, nonlinear finite elements for continuous structures. But chapter 3 of that book is, in my opinion, the most concise review of continuum mechanics I've ever seen. So it's just one chapter in a book, but it's got everything you need there. It follows the notation of Malvern. And so, if you find yourself not understanding everything we're talking about in the class or not following, maybe the single source I would recommend to go to would be chapter 3 of this book, Nonlinear Finite Elements for Continuous Structures. And it's available online through the UT library. You can just download the PDF of that chapter. Should be. So, like I mentioned at the beginning of class, I plan to, so I'll be deriving notes here on my tablet, and I'm also recording. I'm recording the screen as well as my voice. And so there's nothing there yet under the videos and notes section, but as the course progresses, so I'll begin to, every day, once I can process the videos, I'll add them there, and for your reference, they'll be there. So usually takes me about a day, hopefully I can get them done in a day, like 24 hours, because I do have to I'm recording the raw video and then I have to process it to a format that I can go to YouTube. So yeah, a little bit more about myself, and how I learned this stuff. So before I was in academia, I worked for 7 years for Sandia National Labs, government research lab in New Mexico, if you're not familiar. And when I was there, I basically worked on developing finite element models of geomaterials that could exploit the world's largest computers. So the supercomputers there, and that's kind of, how many of you are taking my HPC class this afternoon? A couple of you, right? So that's also how I learned high performance computing was, during my time there. So yeah, I've used all this theory and the computer implementation. I've done it all, written many codes to implement this all myself, So I used to have a pretty good grasp of it. We'll see. We'll see how rusty I am when we get started here. So anyway, are there any questions before we kind of jump into a lecture? Yeah.
What programming language were you using?
Well, back then it was C++ primarily, right? Yeah. Nowadays I would, if I was starting from scratch, I would use Julia. You know that. Yeah.
But for this course?
Oh, I don't really have a preference. There's, it's not going to be automatically graded like in other courses I teach. So it's not. I don't really have a specific language. I would say you can use whatever you're most comfortable in for those problems. I will probably post if I post solutions, which I probably will. I usually try to work the problems before I assign them to you. So if and when I post solutions, they'll probably be in Python. The reason is because most of you probably know Python. Yeah. So if you know anything, you know Python. So yeah, I know, I'm pretty proficient in 6 or 7 different languages. All the engineering languages, MATLAB, Mathematica, Julia, Python, C, C++, Fortran. When I was at Sandia, I used to write some Fortran code. So, yeah, I'll be able to, almost anything. Would anyone be doing homework in any language that I didn't just list? Anything that you will probably be doing your homework in, I will be able to understand. Yeah. Main thing's the answer, yeah, and the visualizations and stuff. So, we may actually also just, when it gets to the kind of final project time, let me ask this. How many of you, I know you haven't seen the problem yet, so it's kind of hard to answer, but like if I'm going to assign you to write a code, what language would you use? Like by show of hands, would it be Python? Yeah, so almost everybody. So those of you who didn't raise your hands, what would you use?
Julia.
Julia? All right, I like you. So yeah, there may be, when we get to the end, we're definitely going to cover some finite element theory, and I'm definitely going to ask you to write a finite element code at least in one dimension yourself. So you just go through the process and understand what it's doing. But there, of course, in languages like Python and Julia, there are finite element libraries. Like in Python, a common one is Phoenix, right? In Julia, you have GridApp or FEMJL. So the final project may be where you don't necessarily need to write all the code yourself. You can just use a library within a language to solve the problem. So you certainly can write it all yourself. Yeah. All right. Any more questions? All right. You ready to get started?